Hi everyone, my name is Xihang. This is our final project presentation. My partner is Boyang and Xihang.
Hi everyone, I am Boyang and Xihang, and I'm gonna introduce our project first. Our final project is all about a map app called Trojan Map. Our map app includes the surrounding area of USC campus and has multiple utility functions, such as the shortest path, cycle detection, and TSV problem, and so on. And we are gonna introduce our functions one by one in the next part.
In the function 1, I will introduce autocomplete function. We will use partial location name as prefix and return a list of possible locations. The whole design is not complex. First, this is a case-insensitive situation. We only need to check first few digits of every location name. Of course, the digits depend on input size. Finally, just return the vector including the possible name. Function 2 has two parts. First, input name and get position. We need to use a for loop to solve this problem. Second, calculate edit distance. This is a classic dynamic programming problem. When entering a location name and does not exist in the map, our function should determine whether the input can be replaced with a similar name or not. We can create a table. In the first column is word 1, first row is word 2. For every character, we have three choices: insert, delete, and replace. There is a special case. If one column and one row has same character, we may skip one operation. Finally, using two for loop, we'll find out the minimum edit distance.
The very next part of our introduction are function 3 and function 4. As we know, some of the places can belong to some categories such as the bar, the library, or the restaurant. So function 3 can go over all the places on the map and return all the possible categories of the places. And function 4 can take a category name as the input and return all the places coordinates in this category. And the next part is function 5, is to get locations use regular expressions. This is very simple, so we're gonna skip it. And the function 6 is the shortest path. So the function 6 can take two places names as the input and can get the shortest path between these two places. For example, if we input Ralph and Target to the function 6, and the output can be the shortest path from Ralph to Target. And the path is saved in a vector. The first item is the Ralph's ID and the last item is Target's ID, and all the other points are the intermediate points on the path. The function 6 can return the whole length of the path and can also mark the green line as the path on the map. So we use two methods to implement this function. The first one is Dijkstra and second one is Bellman-Ford. We mark the average time for these two methods, and we can see that the Bellman-Ford method is a little bit faster than Dijkstra. And the next one is function 7, which is cycle detection. So the function 7 takes a square area as the input and detects if there is at least one cycle path among all the points in this area. For example, if we pick a very small area like this, and the result will be false, and if we pick a little bigger area like this, and the result will be true. The whole idea for function 7 is that we find all the points in the square area first and we perform a DFS on the point. If we hit a point that has already been visited, we can say that there is at least one cycle path in the area. Or if all of the points have been only visited once, we can say that there is no cycle in the area.
Function 8 is a topological sort. We need a direct graph using locations and dependencies. We create a DFS helper function. This is a recursive function. When a child is not marked, we call the DFS helper. Finally, we need to reverse the result and return it. This function is similar to the previous function, so it's not a big deal for us.
The function 9 is a very classical traveling salesman problem, TSP problem. So we can pick several points on the map, and the function 9 will get the shortest path to visit all the points and return to the first point. There's an animation presentation which shows how we find the shortest path. And we use three methods to achieve this function. The first one is brute force. So we find all the permutations for the points and find the shortest path. This is very intuitive. And the second one is backtracking. This is almost the same as brute force, but we stop when the current path is already longer than the shortest path we found in every loop. So this is theoretically faster than brute force. And the third one is tier optimization. We use a random path as an initialization and swap 2 points on the path randomly in every loop. And after every swap, we mark the path if it is shorter, and we stop the loop after a fixed number of loops. And we mark the runtime for these three methods on the different numbers of points, and we can see that the backtracking is much faster than brute force as we expected. And the tier optimization is sometimes faster and sometimes slower, but the biggest flaw for tier optimization method is that it cannot guarantee we get the shortest path every time.
The function 10 is finding nearby locations. We have to find the valid outputs based on the given source location, radius, and the number of outputs. There are 3 steps. First, storing all the addresses related to the attributes. Second, check the distance from the center to the destination. And finally, return the results. You can see that in our slide.
Okay, so these are all the functions we implemented, and there are also some further works we are planning to do, such as optimizing each function to achieve better runtime complexity and also creating an UI for the app. This is all for our final presentation, and thank you so much for watching our presentation. And please do feel free to contact us if you have any questions or concerns. So have a good day.